Hi, this is Jordan Stevens and Danica Dvorak. Unfortunately, we could not get together to do our presentation because it is Easter weekend, and we had our capstone project due this week. This is Engineering 460, Presentation 5. So we're going to be going into Chapter 4, the first section, 4.1. It just goes into the standard normal distribution. So it starts off by giving the form of a normal distribution, and basically saying whenever the mu, the mean, and the sigma are 0 and 1 respectively, they form the standard normal distribution, in which the random variate x is based on mu plus, x is based on the mu plus sigma times the random variate z. Moving on to the next section, we're going to be getting into the Box-Muller method. So basically they're expanding upon the standard normal distribution, where now we have a joint probability distribution where we want to get a x1 and x2, two random numbers, out of a standard normal distribution. So we start off with this form, which is just seen from a standard normal distribution, and they do something rather odd with it, but it works. So what they do is they move the equation into polar coordinates. This works because of the x1 squared plus x2 squared. So they form that into the sine and cosine respectively, and that reduces down to just negative r squared. This can be seen in this line right here, and this is the Jacobian of dx1 per dr and d theta. Also, we need to make sure that we understand that it is in respect with not only one variable, so it's not dx and dx1, dx2, it's dr and d theta. From that, we figure out that the random variable has the form of the square root of negative 2 natural logarithm of a random number. So from this, we can see that solving for r and the inverse of this equation, we get these two equations right here, where x1 is equal to the square root of negative 2 log, natural log of r1 times the cosine, and x2 is times the sine. From this, they take it even further for another algebraic step and see they take a u and a v variable, and they use a substitution with u and v to get it back into the Cartesian coordinates. Actually, it already did happen up here, but they are just moving further to make it into a simpler form. So they see a relationship of not only tan of v divided by u is equal to 2 pi r2, which can be seen right here in these equations. They also see that u squared plus v squared is equal to r1 right here. So from these two, they basically just plug them in and do some simple algebra, and they get these two easier forms to plug values in. So you randomly generate a u, you randomly generate a v, you plug them in, and you get an x1 or x2 that you output from it. Moving on from this, they push into an improved envelope projection. So they are using a joint probability distribution rather than just using one variable. This improves the acceptance rate for the rejection. So they start off with a typical problem. They want to do a normal distribution, and they have a majorizing function of the lambda e to the negative lambda x minus c here. So that would be the exponential distribution, and the exponential distribution can be inverted, so that's why they do this. From this, they get this equation, and this is just from chapter 3, I think, and this is just the standard process they use. We of course have to maximize. We have to use c and lambda such that we maximize the distance, minimize the distance between them. Sorry, minimize the distance between them. From this, they form the one for r1, so they get this piecewise function for these three equations. They invert these three equations going to this arrow right here. So if you were to plug this into a program, If R1 is less than 1/4, use this formula. If it's between 1/4 and 3/4, use this formula. And if if R1 is greater than 3/4, use this formula. This piecewise function will envelope the normal distribution and reject it such that the exponential distribution forms into the normal distribution. From this, though, they add an extra little point. Let's say that we are given a second random number, a prospective variate x, they say. This is another half to the equation, such that if we have a Box-Moeller distribution and we were to get R1 or R2 popping out of that equation, we get R1 going to that equation above, and we get R2 going to this equation. This equation kind of has the same exact logic. They're using the exponential. They do something a little weird here too, which is the x squared divided by 2 minus lambda times the absolute value of x plus lambda c. From the book, it just seems they seem to throw this in here. They say it algebraically works, but they don't really give an explanation. They do give a source or two to back up what they're saying, though. But from this, we see that our R2 is within these bounds where it's squeezed between this and this value. Going on to the next section, we just go into the log normal distribution. They just kind of explain what a log normal distribution is. Basically, it's y is equal to e to the x. We can find that the mu, or the mean, and the sigma are found through these equations right here. So this kind of actually looks like the normal a little bit. This is the expected value of y times something that kind of looks like the normal. But we can definitely see that it looks very, 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 very similar to the normal once we get to this side and get this equation out. It seems like it's a variation of normal distribution. This distribution is used a lot in the finance industry, and it will be used in the next couple sections. I've seen that it's been used in a little bit in Brownian motion in our homework. So with that, that is it. Thank you.